Just drawing out the tree diagram. Remember, each set of branches is an event. So, first set is opening the first cereal box. Okay, second set, opening the second cereal box, and so on. Okay, and it's prize or no prize. So I'll do P and then this prime symbol. What's the name of this prime symbol in probability?
Complement.
Complement, yeah, good. Obviously, we know that it means the opposite of getting a prize, but yeah, it's the complement. Okay, and these are all 0.2s and 0.8s. Why isn't this probability changing as I go on? Good. What's the name for that in probability? Independent. These are independent events. Opening one box and looking at whether there's a prize in it does not affect the next one. So here we go. Really simple probability tree. All the probabilities are the same. You don't need to think, oh, I need to take one off there and not there. Much easier. So what's the probability of getting exactly 2 prizes? When they say exactly 2, it means not 1, not 3. It's got to be just 2. Which roots are we looking at? Missa?
The very top one.
And then down. That would be the very top one?
Yeah. And then also starting with the same one, but then going to the no prize and then back up to prize.
Yeah.
And then the final one is starting with no prize and then up with prize and another prize.
Okay, there are no other routes, are there? Just those 3. Okay, so how do I find the probability of those? Girls, how did you start doing this?
You just multiply the different probabilities.
Oops, let's go with that.
And for each group, it's 0.2 times 0.2 times 0.8 in various order, but they all have those different probabilities.
Okay, and what's that equal to?
0.032.
0.32. Okay, so yeah, one thing I overheard. No?
Oh yeah, that's it individually. Yeah.
One thing I overheard Missa and Fabi saying is that it's going to be the same numbers when we look at the orange route, just in a different order. Okay, and the blue route is going to be the same numbers, just in a different order. And when we're multiplying, it doesn't matter. So they're all going to be 0.032. Okay, so how do I find the probability? How do I finish that question off?
Multiply by 3.
Okay, yeah, we're going to add the 3 up, or we're going to multiply by 3. Yeah, so probability that we have 2 prizes is 3 times 0.032. Super. Okay, so far, not too challenging, I hope. But what happens if we increase the number of cereal boxes? What happens if we had 5 cereal boxes? How's this going to change? How's it going to stay the same?
Well, then if there are 5, there would be 5 different terms that you'd be multiplying together.
Okay.
So probability 1.
Good. There will be 5 turns because we've got to open 5 cereal boxes. Notice when we did this yellow branch, we didn't go, oh, it's 0.2 times 0.2, and I've got my 2 prizes. We still had to include not getting a prize in the third one. Because what might have happened, if we'd just done 0.2 times 0.2, we might have got a third prize, and that isn't exactly 2 prizes. Okay? So there are going to be 5 terms we're multiplying together. If we're going to stick with winning exactly 2 prizes, what are those 5 terms going to be, Arabella?
So we'd have the same and then times 0.8 times 0.8.
Okay, we're going to have 0.2 times 0.2 times 0.8 times 0.8 times 0.8. Right, but we're all doing SL maths, so let's write this with some powers. Make it neater. How can I simplify it using
0.2 squared times 0.8 cubed.
0.8 cubed? Oh, and look, 2 and 3 make 5. Does that seem familiar? Yeah, that's kind of what we were finding with the binomial theorem, is that those powers add up. What's our next thing that we've got to solve? Because this isn't the answer to the problem. This is a really small probability. What's our next issue?
To know how many times there are.
How many routes? Yeah, how many paths are there? There were 3 here. Are there just going to be 5 this time?
We don't know.
We don't know. What we're actually doing, though, is we're seeing how many ways we can choose 2 objects from a group of 5. How many ways we can get 2 prizes out of 5 cereal boxes.
I mean, maybe you can assume so, because for that one it says you buy 3 cereal boxes, and then there turned out to be 3 paths. And then when there'd be 5, maybe there'd be 5 paths, but you can't necessarily assume that.
No, you can't. One thing you could do is draw out the tree diagram, but that requires a lot of branches. Yeah, there'll be 32 branches at the end. It's Pascal's triangle. This whole idea of choosing objects from a group is our combinatorics, isn't it? So what we're wanting to do is we're wanting to have 5 objects and choose 2 of them. And this is where we were getting the coefficient for our binomial theorem. So this will be the number of paths that lead to 2 prizes. What is 5 choose 2? Laura, how would you work out 5 choose 2? Or the triangle. Yeah, either way. And it is 10. Okay. So there are 10 paths that will lead us to exactly 2 prizes and 3 cereal boxes with no prizes. All of those paths will have 2 0.2s and 3 0.8s multiplied together in various different orders. Okay, so to answer this question, what is the probability? We're going to have to take this probability of getting it in one path and times it by 10. So this time the probability of getting x equals 2 wins, would be, I'm actually going to write it like this, because this should seem familiar to what we were doing last week. 5 choose 2 times 0.2 squared times 0.8 cubed. Arabella.
Why don't we do 5 choose 3?
Why don't we do 5 choose 3?
Because the cubed on the 0.8 is a 3. Why do we choose the 2 and not the 3?
Because we're going to win 2 prizes.
Yeah.
The general term.
Yeah, it's okay. Yeah, I see you're making the link with what we're doing with the theorem. Yeah, it's not the general term. So if we think through that whole fact that there was an extra term, it makes a bit more sense in this context. You could have 0 prizes, 1 prize, 2, 3, 4, or all of them could be prizes. So we're going to get 6 different possibilities. So I think this is quite a useful example for that.